going live, I believe. Good. Finally. Good. So this took a little bit. So again, I apologize for the delay. This was due to my HDMI capture card just failing on me for whatever reason. So I had to downgrade my setup. So yeah, we have video, I hope. So you can see me in Zoom, right? And hopefully you see me on YouTube as well. And there might be some audio-video synchronization problems. I hope it's not too bad. Unfortunately, I won't be able to fix it right now. So anyhow, all right, let's start. Today, I'm here to give a live talk on this topic and repeat my SIGGRAPH talk on a class of C2 interpolating splines. Give a basically live version of that. It's going to be slightly different, of course. And this is a part of the University of Utah graphic seminar series. So we're going to kick off this seminar series with this talk, and then there's going to be other talks. So this talk is streamed on YouTube, and there are a few people watching it on YouTube, and but not necessarily all talks will be streamed on YouTube. We'll see how that will go. All right. So yeah, this is the topic. I think I can just jump into it. So before I start, let me tell you that this is designed to be an interactive talk, so feel free to interrupt me at any time with your questions. Those of you watching on YouTube, my student Dajalin is actually following the YouTube chat, so you can type in your questions if you want to. And if you're in the Zoom meeting, you can just speak up, and I'll be able to hear you. So don't worry about interrupting me. All right, so this talk is going to be again on a class of interpolating splines. And what's important is the properties of this class, right? So all curves in this class have certain properties that make them nice. They have C2 continuity, local support, and they don't require any global optimization, solving any global optimization problem. And I'm also going to talk about some example curves within this class that have some very, very nice properties, like no self-intersections, well-bounded, well-defined bounds, and they can form perfect circles and ellipses and lines. So, but let me start with, like, why do we care about this in the first place? I'm going to tell you quite a bit about how curves are formed. I'm going to give you the necessary background. So if these terms don't make any sense to you, don't worry about it, for the time being anyway. But curves I want to start with curves and splines. They have very wide range of applications. I'm going to talk about them in the context of computer graphics, but curves have applications way beyond computer graphics, right? So they can be used in all sorts of different things. And the particular type of curves that I'm going to talk about in this talk are going to be interpolating curves. And interpolating curves have been quite difficult to use properly. They're very nice curves in some ways, and they're kind of difficult to use. So this formulation that I'm presenting today is a way of sort of solving all these long-standing issues of interpolating curves. So before we go into details of this formulation, let me go through the background. Like, so for those of you who may not be familiar with the details of how curves are defined, let's go through that a little bit. So when I say curves, I would like to make this point first. Probably spline is a more appropriate term, but in the context of computer graphics, curves and splines are basically, they oftentimes mean the same thing. They don't have to, but they oftentimes mean the same thing. So I find myself using the term curve more often than spline, but I actually mean the same thing. So don't pay attention to which one I'm using. So curves are typically defined, at least in computer graphics, they're typically defined using a set of control points. They don't have to be. There are actually different ways of defining curves as well, but they're typically defined by a set of control points placed in space in a particular order. And the curve that is defined by these control points can be what we call an approximating curve. Its shape is defined by these control points, but an approximating curve is not going to go through these control points. These approximating curves used in computer graphics are actually very, very nice. They have very nice properties. They're used very often. But, you know, obviously they're not going through the control points, so it's kind of difficult to precisely control exactly where the curve is going to go through. So they're not useful for all applications. In some applications, you really want what we call interpolating splines, interpolating curves. They actually do go through the control points. So that's very nice. But because they're trying to go through the control points, they do some crazy things. And I'll tell you what I mean by those crazy things. And because of these issues that interpolating curves have, they're not as popular to use in computer graphics. But we're going to solve that problem today, so don't worry about it. So another very, very common formulation of curves is Bezier curves. So you can think of Bezier curves like in between interpolating curves and approximating curves. I would call it more like an approximating curve. Because a Bezier curve, let's say a cubic Bezier, for example, will be defined by 4 control points. And the curve will interpolate the first and the last control points. And the other 2 control points in the middle will just define the shape of the curve. Right? So it's just a quadratic Bezier. If you have, sorry, this is a cubic Bezier. A cubic Bezier will have 4 control points. It's a cubic function. A quadratic Bezier will have 3 control points. Higher degree polynomials will have more and more control points in the middle, but they will always interpolate the first and the last control points, right? And if you want to have a longer curve, not just one curve piece like this, we're going to have a piecewise Bezier curve. We're going to attach multiple Bezier curves like this, and you can have a longer curve like that. So that's very nice. And it all works out fine. So what's the problem with that? Well, the problem is that we have these control points in the middle that are not interpolated, right? So our curve is not just defined by these the control points that the curve is going through, but we have these additional control points that the curve is not going through that we also need to worry about to define the shape of the curve. And that adds an additional complexity to it. Beyond that, if you want to have something like C2 continuity with these curves, you need to be very careful about how you place these internal control points such that we get C2 continuity where the 2 curve pieces join here. And that's going to be very, very difficult to do this manually, like manually setting this right so that we get C2 continuity. So what do I mean by C2 continuity? Let's talk about it just a little bit. Starting with C0. C0 means that our curve is just one long piece. It's not made up of multiple pieces. So basically it says at this point, the 2 curve pieces join together exactly at the same point. That's C0. If the curve is C1, that means the tangent of the curve at the point where they join is going to be continuous as well. Well, we're looking at the point where they join because everywhere else is defined by the formulation of the cubic Bezier. So yeah, it is going to be C1 anywhere else. But what's going to be tricky is going to be right at this point where the 2 curve pieces join. And C1 actually means parametric continuity. If you just worry about the direction of this tangent, not the length of the tangent, we're going to be looking at G2 continuity. G2 continuity is the geometric continuity. That means geometrically the tangent direction is the same, but the length of the tangent may not be the same. So what do I mean by length of the tangent? What I mean is the derivative of the curve. The derivative of the curve formulation will give you the tangent, and the length of that vector may not be the same when they join. So actually these two terms, C1 continuity and G1 continuity, they are very closely related. You can take any curve that has G1 continuity and you can reparameterize it. That is, you change how fast the curve parameter is moving along the curve without changing the shape of the curve at all. And you can convert a G1 curve to a C1 curve just by changing how fast the parameter is moving. So they're actually very, very closely related terms. Going along, if you look at the second derivative, that's going to be C2 continuity. The second derivative means that the tangent, the change of the tangent is going to be continuous along the curve. So it's not just the tangent where they join, but also how fast the tangent is changing is going to be continuous. And again, we have G2 continuity versus C2 continuity, and they're closely related. Now, why do I care about G2 continuity or C2 continuity? Because that's going to define whether the curve has curvature continuity. If the curve does not have curvature continuity, you might be able to recognize these separate pieces. But if it has curvature continuity, then it was going to be very smooth, and you won't be able to tell where the two pieces join. And that's, for a lot of applications, that's actually very, very important. There are other properties of the curvature as well. Like the curvature, let me talk about that. Curvature is defined by the circle that you can fit at any point. So at this point, I'm fitting a circle, and the curvature is defined by the radius of this circle. Actually, it's 1 over the radius of this circle. So if the curve has curvature continuity, this circle that you put on a tangent of the curve is going to change its radius smoothly or continuously, right? Not necessarily smoothly, but continuously. That's what G2 continuity means, and that's what curvature continuity means. So depending on your application, C2 continuity can be vital, very, very, very important, or sometimes you don't care about this. So the types of curves that I'm going to talk about today, they're going to be curves that have a guaranteed C2 continuity everywhere. So we're going to have this property. So these curves are going to be very suitable for applications that require C2 continuity. Right? But these are not all the properties of curves. There are other stuff. For example, local support is a very, very important one. Local support means that any piece of the curve, let's say like this piece, this curve piece, will be defined by only the control points that are around it. So it doesn't have to be just these 4 control points, but there's going to be a finite number of control points around it that will define the shape of this curve piece. And it's not going to, the shape of this curve piece is not going to change when you change some other control points. So it's going to be defined locally. That's actually a very, very important property. If the curve does not have local support, that means it has global support, in which case, if I move 1 control point, the shape of the entire curve changes, which is, of course, not a desirable property. For a lot of applications, that creates extra complexity. And you like the shape of the curve around here, when you want to change the shape of the curve somewhere else. And as you move 1 control point, the whole curve changes shape. This is obviously not desirable, right? Another important property is whether the curve is bounded or not bounded. Here's what I mean by that. Imagine a curve piece that connects 2 control points. So if the and the line, imagine the line that goes through the 2 control points that the curve piece interpolates. So if the distance of the curve, the maximum distance of the curve from this line is bounded, if there's an upper bound to it, depending on the distance between these 2 control points, regardless of where the other control points might be, then this curve, I will call this curve bounded. And this is a very nice property that means that the curve is not going to deviate and form undesirable shapes. And it's going to be always within this region, regardless of where the other control points are. If it's unbounded, of course, the curve can be anywhere, which is not a desirable property. So looking at the properties of prior curve formulations, these self-intersections and unbounded curves are actually very, very common with CT interpolating curves. And self-intersections create some strange features like this. And this is the kind of stuff that you really don't want to see, because if you wanted to see it, you would place your control point such that you would get it. This is an artifact of your mathematical formulation, really. This is not something that you're trying to achieve by having an interpolating curve. So this is bad, and we don't want anything like that, self-intersections or cusps. And we would also like the curve to be bounded, so you don't want it to go to infinity if it wants to. So early on in my much earlier work, I worked on this topic of interpolating curves, specifically about Kaplan splines. And together with Scott Schaefer and John Kaiser, we've shown that Kaplan curves with a particular parameterization technique applied to them guarantee that the curve is not going to have any self-intersections and the curve is going to be bounded. So more specifically, the centripetal parameterization. And I'm not going to go into the details of what centripetal parameterization is because it doesn't really apply to the curves that I'm going to talk about. It applies to Kaplan splines. So in the context of Kaplan splines, centripetal parameterization actually gives us these nice properties that the curve is not going to have self-intersections and it's going to have bounds, but this only works for C1 curves. If you go to C2 curves, these properties are not supported, so not so good. So again, the question here is that do you care about C2 continuity? If you want curvature continuity, that means you want C2 continuity or at least G2 continuity, then that's not going to be good enough. But for my purposes, those curves were nice, and I pretty much stopped thinking about this problem until this paper came up. So these kappa curves, a recent curve formulation that was presented at SIGGRAPH. So these curves are not C2, but they're G2, so they're good enough. Well, actually, they're mostly G2. When they're inflection points, you can't make them G2. So at that point, they break the G2 continuity. But for most places, it's G2. So they're very, very nice curves. They're 2D curves, but they're very, very nice curves. What is the problem here? Well, the problem here is that unfortunately they require some solving some global optimization problem. So here's what I mean. You have your control points. To be able to form these curves, you need to solve a numerical optimization, and that gives you the parameters of the curve. And which is okay if you have just a couple of curves, but if you have a lot of curves, like I don't know, maybe you're defining a Young level cloth model or a hair model or something like this, you have lots and lots of curves. This global optimization is going to be a problem. Also, these curves are 2D only, so you can't use them for those purposes anyway. So they're okay for what they're invented and what they're designed for. Another thing is that they don't quite have local support because you're solving a global optimization problem, right? But turns out it's not a practical problem because even though they technically don't have local support, the impact of a control point is mostly local, even though there's non-zero impact elsewhere. But most of their impact is local, so they're okay in that sense, in practically okay. Well, they can't firm circular and elliptical arcs. Actually, when your curve formulation is polynomial, if you define your curve using polynomials, you won't be able to define perfect circular and elliptical arcs because circles are not polynomials. There's a way to get around it. Actually, you can have rational polynomials, and rational polynomials are a little more complicated, but not too complicated. And it's possible to extend kappa curves to use rational polynomials, in which case you can get circular and elliptical arcs. Although, when you go to rational polynomials, you add an additional dimension to your curve formulation. That adds another degree of freedom to all of your control points that needs to be adjusted such that you get the circle that you want. So it adds quite a bit of complexity that I personally don't like. So the rational polynomials are okay, but it'd be good to solve these problems without using rational polynomials. Another thing is that linear segments. For most prior curve formulations, forming linear segments is not a problem at all. But when you have a global numerical optimization, and when you're trying to optimize for other things, you can actually sacrifice the possibility of your curves ever forming linear segments. Actually, that turns out that's what happens with kappa curves, which is not very nice. And of course, as I said, they're also 2D only. A lot of curve formulations are, well, there are a lot of interpolating curve formulations that are 2D only, but there are also a lot of interpolating curve formulations with not so nice properties that are 3D, such as kappa norm curves that are totally 3D. All right, so that's the background about curve formulations. Do you guys have anything to ask at this point? All right, if not, I'm moving on. All right, so now let's talk about this class and how we can solve all of these problems of prior interpolating curve formulations. Right. So this class of interpolating splines that I'm going to talk about today, they're defined by two functions. The first one is an interpolation function. The interpolation function takes three consecutive control points, and defines a curve that goes through these three control points. Let's call it Fi. That's the ith interpolation function. Now, there are various ways of defining this interpolation function, and I'm going to talk about some alternatives. And depending on how you define an interpolation function, you get a different curve formulation in this class. And I'm going to give you examples of that later on. At this point, suffice it to say that there are various ways of defining them, and it's a very simple process, right? You just need to pick a function that goes through three chosen control points. The other function is the blending function. Sorry, before I go to blending function, let me define the parameterization that I'm going to use for defining these interpolation functions locally. So when when the parameter is 0, a local parameter is 0, the curve is going to be exactly at this point. When it is at pi over 2, it's going to be at the middle control point, and when it is pi, it's going to be at the other control point. Now, this is what we call a local parameter for this function. It just takes one value, basically, and outputs a vector position in whatever dimensions that you're working in. So this parameter value is defined locally like this for this interpolation function. And we can also define a global parameter value for the entire curve. So when you have multiple curve pieces joined together. And that's actually fairly easy to do. But this is I just want to draw a distinction between a global parameter and a local parameter. This is a local parameter that we're going to be using for defining these interpolation functions. So this was the interpolation function. What's the blending function then? So the blending function will take two interpolation functions. It's in this case Fi and Fi plus 1. And it's going to blend between them. So it's going to interpolate the two interpolation functions, the result of the two interpolation functions. And it's basically going to form, by doing so, it's going to form a piece of the curve. So this is the piece of the curve that's going to be defined by these 4 control points. Right? And it's all done by the blending function that blends the two interpolation functions. The nice thing here is that just with this formulation, with this construction, we get a perfect local support. So like a curve piece is defined by only 4 control points, which is really nice. I mean, you can't possibly expect to do anything better. Like, can I do with just 3 only? I can't. Yeah, I can't expect to get C2 continuity in any way if I'm only looking at 3 control points, right? So 4 is like the bare minimum that you could possibly get, and we're getting that. So that's great. So it has perfect local support. So, all right, let's take a look at this blending function. Like, how do you blend these two interpolation functions together? Actually, most of the secret in this formulation is hidden in the blending function. Now, there are different ways of defining a blending function. You can apply different formulations. The particular formulation that I use in this paper is this trigonometric blending. So cosine square times 1 value sine squared times the other value. So the if you look at it, the curve parameters are shifted by this one's shifted by pi over 2, so that when theta is 0, this theta is 0, f1 fi is going to be at this point, right? And fi plus 1 is going to be at this point. Did I just write this wrong? No, I didn't write it. No, did I write it wrong? No, I didn't. I didn't write it wrong. Sorry, I just confused myself. Let me repeat this again. When theta is 0, fi is going to be right here. And when theta is 0, fi plus 1 is going to be exactly at the same point, right? So they're exactly at the same point when theta is 0. When theta goes to pi over 2, again, they're going to be exactly at the same point. And in between the two, we're going to use trigonometric blending. Now, of course, when theta is 0, cosine squared becomes 1, sine squared becomes 0, so this term disappears. So I don't really care where this point is at that point. So it's just coming from one of the interpolation functions. Same goes for this point. You know, in this case, cosine disappears. We only have sine, but they're smoothly varying between the two, which is what we want. Now, the nice thing here is that this particular interpolation function, this particular blending function, will allow us to guarantee C2 continuity without worrying about how these interpolation functions fi and fi plus 1 are defined. Regardless of how they're defined, we will be able to get C2 continuity. Well, of course, they should be C2 continuous themselves, of course. And here's why. Because of this formulation, it turns out that when I look at the first derivative and second derivative at this point and this point, where the curve pieces will connect to the next curve pieces, at these points, the derivative of the curve and the second derivative of the curve only depends on one of the interpolation functions. So at this point, it's only going to depend on fi, and at this point, it's only going to depend on fi plus 1. And that's because of this blending function. So if you take the derivative of this blending function, and if you put theta is equal to 0, you will see that all terms that include fi plus 1 is going to cancel out in the derivative, just like in the regular formulation. And also in the second derivative, they will disappear, not in the third derivative. So these curves are going to be C2 continuous. So if you could infinitely many times take the derivative of the curve, and in that case we would have C infinity curves. We're not getting C infinity, we're just getting C2. So the first derivative and the second derivative at these endpoints will depend on one of the interpolation functions, and that's how we're going to get the C2 continuity, right? So that's the trick. The derivative of the curve depends on the derivative of the interpolation function. In this case, t is the global parameter. Okay, good. So all we got to do now is just to pick an interpolation function, right? Well, let's not go there just yet. There's a bit of similar prior work, and so it turns out I'm not the first person to come up with this idea that we could just blend two curves together and get something nice. But it's not a very common idea, it seems. Actually, I had no idea that this thing existed, and I did quite a bit of research to figure things out, but I couldn't find. But luckily, when I submitted this paper, the reviewers said, "Hey, there's a tech report from 1968." So thank you if that reviewer ever watches this video. Thank you. This was super helpful. There's no way that I would be able to find this on my own. So this was great. So this is a tech report from 1968 and talks about the very idea of blending two parabolas. So, okay, it's not exactly the same, but it's a very related idea, right? So you take two parabolas and you blend them to form a curve piece, which is, in the same spirit, right? Of course, because it's dealing with parabolas, the properties of the curves you get out of this formulation, they're not very nice. So that's the reason why probably people didn't look at this idea too much. But actually, a couple of people did. A couple of people published curve formulations that are related, and they actually ended up using exactly the same trigonometric blending function that I'm using in the paper. So these three papers listed below here, they define curves within the same class of curves that I'm describing in the paper. But unfortunately, the properties of these curves are not so great, and that's why they didn't become popular. Is what I'm guessing. So I'm going to talk about all three of them later on. All right. So let's move on and finally talk about some example interpolation functions. So in the paper, I'm describing 4 example interpolation functions. So I'll just go over them quickly. The first one, and probably the most familiar one, is the Bezier interpolation function. And the Bezier interpolation function is going to use a quadratic Bezier for defining a curve that goes through these 3 control points. Now, a quadratic Bezier is defined by 3 control points. So what I'm going to do is I'm going to take the first and last control points to the first and last control points here. And this middle one, well, I'm going to pick a position such that the curve goes through this desired middle control point. Now, obviously, if I take this middle point, and put it on top of this control point, the curve is not going to go through here. So that's not what I want. I want to have an interpolating curve, so I need to carefully pick a position for this. And there's actually it's very easy to pick a position for this. There's actually infinitely many positions for this. There isn't just one. You can pick a whole bunch of different positions in space such that the curve will go through this. Now, if you're not careful about how to pick this point, the curves you're going to get are not going to have nice properties. So here we're going to be very careful. And the way we're going to be very careful is that we're going to pick a point such that when I look at this quadratic Bezier here, the maximum curvature along this curve is going to be exactly at this point. So I'm picking this control point position. I'm picking this position such that I get the maximum curvature at this point. Like, how do I do this? It's not too hard. If you write down the curvature equation for a quadratic Bezier curve, you can actually find the location of the curvature maximum, and that gives you a cubic equation. And that cubic equation is guaranteed to have a maxima. Well, there's going to be a maxima, either one of these control points or over here. So you're going to have to solve a cubic equation to get the position of this point. So it's not too simple, right? There is a way to solve a cubic equation in constant time, although it's a little complex. The way I implemented this was I just used bisection numerically, and I numerically found this position, but it's just solving a cubic equation, a single cubic equation, right? So it's not in that case. Well, I guess it is constant time because you picked the constant with bisection, but it's not a super cheap, just a couple of multiplications kind of solution to find this position. But it's not something very expensive, like you're solving a global optimization problem involving all of the control points. It's just 3 control points, a very, very simple equation that you're solving. So not too hard, but not super cheap either. Right, so there's going to be some cost associated with that. But if you do that, your curves are going to have very nice properties. The curves are going to be bounded. So if you look at the maximum distance between these, between the curve and the line that connects the 2 consecutive control points, they're bounded actually with this ridiculous bound, like 1/8 of the distance. So they are very, very tight. They're very, very close to what we call the control polygon, the line segments that connect the consecutive control points. And you'll see when I show you some examples that these curves are very, very close. They're almost like, they're not quite like line segments, but you can pretty much see where the control points are. So they're very tight. This is a very tight bound. Maybe a bit too tight actually, and you'll see that in later on. The other thing is that the tangents, if you look at the tangent directions on either control point, they will always be pointing towards the next control point. Here's what I mean by that. Like if I look at this direction, the direction towards the next control point, and this is going to be the opposite direction. They will always point towards the next control point. They will never point this way. And this is actually a very, very important property. And this also guarantees that, well, it's one of the conditions to guarantee that the curve pieces will be contained between these 2 points. So if I look at in one dimension over here in this direction, the curve piece is going to be between these 2 bounds, which is great, right? So that's what you would expect the interpolation to be. And these 2 properties are required to make sure that we're getting a curve that's not going to form self-intersections. We definitely don't want self-intersections. Another nice thing that comes out of this formulation is that if you look at the curvature of the curve, so this is a visualization of the curvature. So the length of these line pieces show you the magnitude of the curvature at the corresponding point along the curve. So over here we have high curvature peaks, and over there we have curvature peaks, and over here we have like zero curvature almost. So if you look at the curvature peaks, they're actually very close to the control points. They're not exactly at the control points. And I'm saying this because kappa curves guarantee that the maximum curvature will be exactly at the control point, which is a very nice property. I'm not sure if it's a crucial property. It's a very nice property nonetheless. We're not going to quite get that, but we're getting something very close to it. Like the curvature peaks are close to the control points. So that might arguably make these curves sort of more intuitive and relatively easier to control than other interpolating curve formulations. The not so nice thing about this formulation, however, is that because it's based on quadratic Bezier, it's not going to be able to form circular arcs. So if you want to form any circular shape, you won't be able to get it. Actually, it's beyond that. With quadratic polynomials, you can approximate circles to a certain extent, but because of the way that these curves are constructed, they're really not going to be a very close approximation. And you'll see that. I'll show you some examples. Now, switching to rational Bezier curves, using rational polynomial formulation, we would actually get around it, and we could form conics, any kind of conics, but that adds an additional dimension, which is something that I would like to avoid. But it is possible to do. The difficulty is, I'm getting a conic, but which conic am I getting? Is it the circle that I want or not? And kind of need to adjust the parameter accordingly. It adds a little bit of extra complexity that I personally am not a big fan of. All right, this is Bezier interpolation function. If you want to get circles, we can do something like a circle interpolation function. So here's how it works. 3 points in space in whatever dimension. You can define a circle that will go through these 3 points. So if you do that, you get an interpolation function that can easily form perfect circular arcs. Everything's good, right? Yeah, we got perfect circular arcs, right? What more do you want? Well, everything else. So this is very nice, but everything else about this interpolation function is not so great. I mean, this is a constant time operation. You can form this circle, you can compute this circle equation very, very easily. But if you look at the other properties of this interpolation function, you don't get something nice. So the curves are definitely not bounded. They can actually go to infinity. You get self-intersections as shown here. And so, they don't really form very nice interpolation. Like, imagine I have these 4 control points. You wouldn't imagine an interpolation curve that goes and does something crazy like this, right? So these are not very nice curves. And remember I was telling you about earlier work on this topic, like blending two curves to form a curve formulation. So two of the 3 are actually defining this very curve type. So these curves are identical to the curve types, mathematically identical to the curve types defined in these 2 papers. There's one more paper, I'll get to that in a little bit. So, okay, these curves are not very nice. Can we do something better? So I started thinking about this problem. And I thought, you know what? Maybe using something like an ellipse will solve this problem. Well, 3 points in space, that defines a circle, but 3 points in space will not define an ellipse. You need a lot more information than that. So we kind of need to figure out a way to pick a unique ellipse somehow. And the way that I decided to do this is that I added some extra constraints. So I said that I'm going to form an ellipse such that these major axes of the ellipse will be such that the 2 of the control points will be on these major axes. And the way I'm doing this is that I'm looking at the distance between the control points, these 2 control points, and then I'm looking at the distance between these 2 control points. And whichever one is further away, I'm going to pick that one and put it on one of the major axes, and the other one I'm going to put it on the other major axis, right? So I'm defining an ellipse like this. Well, actually, there are infinitely many ellipses that will have this point and that point on their major axes. So that's not sufficient either. What I need to do is I need to pick the one ellipse that will not only have this point and that point along the major axes, but also it will go through this control point, right? Otherwise, it won't be a valid interpolation function. So that's what I'm trying to form here. So all of the ellipses that have this point and that point in one of the 2 major axes, the centers of these ellipses, they are on a circle that go through these 2 control points. So this line from one control point to the other is going to define the diameter of that circle, and the center of the ellipse will need to be somewhere along this circle, right? But I need to figure out exactly what point will give me an ellipse that will go through this control point. Well, I am solving that again using bisection. It's a finite range, and you can solve that numerically with bisection. So that adds some extra computation. It's not just a few multiplications and division or anything, but that's not very complex. I'm not solving a global big numerical optimization or anything. But still, there's a non-trivial cost associated with that. Even though it's fast, even though it's cheap, it still has some non-trivial cost to figure out where exactly this point is. Right? But once I have this point, then I have my ellipse, and if I have my ellipse, I can easily define an interpolation function using that ellipse. And so when I do that, one nice thing about these is that I can get perfect circular and elliptical arcs with this interpolation function, but it will only happen in special cases. So I need to strategically place my control points because I restricted where the control points can be. They're going to be along the major axes of the ellipses. So if they are along the major axes of the ellipses, then yeah, I am going to get perfect circular and elliptical arcs for the final blended curve. Otherwise, you know, I'm going to get something else. And these curves are also bounded, which is very nice. They have a very, very nice bound, actually. Not as tight as the quadratic Bezier interpolation function, but you know, they're still pretty good, right? 21, less than 21% of the distance between the two control points is what I'm getting. And they're guaranteed to have no self-intersections, and if they have no self-intersections, that means we have the other two properties. That is, the tangent is towards the next control point along this direction, and that the curve pieces will be contained in this finite range. But if you look at the curvature behavior of these curves, you don't get something nice, unfortunately. With these curves, I'm getting something not so great. So I'm getting these strange curvature peaks between the control points. This is not so nice, and I'll show you some examples that will probably make it clear why this is not nice. Is that, but let me try to explain. When I define this curve using these 4 control points, I just want to have an interpolation that goes through these 4 control points, right? But the curve shape that I'm getting is creating these visually recognizable features here in the middle, right? And you know, they don't align with my control point data or anything. So I'm getting these visually recognizable features, and it's not a part of my data. So you know, it's definitely not something that's desirable. I mean, this is not as bad as getting self-intersections or unbounded curves or anything, but it's still something bad because I'm adding some visually recognizable features when I don't really necessarily want them. So, can we figure out a way to get rid of them? Turns out, yes, and not too hard. So here's what we're going to do. We're going to combine the concepts of circular and elliptical interpolation functions, and we're going to get a hybrid interpolation function. So here's how it works. Let's say that I have these 3 control points to define my interpolation function, right? And you know, I can easily find the circle that goes through these 3 control points. And now, what I'm going to do is that on this circle, I'm going to look at this angle between the control points. So there's a smaller angle, there's a larger angle here. And I'm going to look at the larger angle, the largest one of them. If the larger one is greater than, if it's greater than pi over 2, if it's exactly pi over 2, I have something nice. So at this configuration, the circular interpolation function will give me this shape, right? And the elliptical interpolation function will give me this ellipse. This ellipse is going to be a circle, right? Because the 2 points are along the major axes. So the 2 interpolation functions, they're giving me the same shape. So it's all good. But when this point it goes away from here and I get an angle that is larger than pi over 2, then at that point, my circular interpolation function starts doing stuff that I don't like. It's going really far from the control polygon, right? So it's going really far from these lines, from this line segment that interpolates the 2 points. On the other hand, my elliptical interpolation function gives me something really nice. So this is pretty good. It has nice properties too. It's all fine. So in this case, I'm going to switch to elliptical interpolation function. I'm going to use elliptical interpolation function. If this angle is smaller than pi over 2, in that case, my elliptical interpolation function is creating these things that result in these curvature spikes that I don't like. But my circular interpolation function defines this nice, tame circular arc, which has no problems, none whatsoever. So in this case, I'm going to switch to the circular interpolation function. So basically, the hybrid interpolation function will switch between the circular and elliptical interpolation functions depending on that angle. So the resulting curves will be bounded because we sort of eliminated the case when the circular interpolation function was becoming unbounded. And it has no self-intersections because we're eliminating the cases when the circular interpolation function can have self-intersections. In those cases, we're switching to elliptical interpolation function. Tangents, again, are towards the next control point, and the curve is contained between the data points. And they're very easy to form circular arcs because now that we're sort of introduced circular interpolation function, in any case where the angle is small, we will be able to get nice circular arcs. So forming circular arcs is almost as nice as circular interpolation function. So that's actually very, very good. And the curvature maxima, if you look at them, they end up close to the control points. They don't have to, like they can move around, like if the curvature is almost the same all over the place. So they don't have to be very close to the control points, but they're not very close to the control points if the curvature is like near constant. In a circle, it's going to be constant, right? But if you have some strong curvature spikes, they end up being close to the control points, which is a nice property. It's not perfect; they're not exactly on the control points, but they're very close to them, which is nice. Okay, so let's see some results, and hopefully I'll be able to persuade you that these are actually nice curve formulations. So let's start with comparing these 4 interpolation functions with this simple shape. So there's if you look at these 4 interpolation functions, there's an odd man out here, right? So this guy here, the circular interpolation function, is the one that's doing something crazy. So the other 3 are doing something reasonable, going through the control points, but this one is creating these crazy stuff. So all these 4 interpolation functions, this is really not the one to use. The others maybe this, no. Okay, so this was a very simple case. Let's take a look at something a bit more complicated than this. So in this case, I'm showing the hybrid interpolation function. These are control points on the hybrid interpolation function, and this is the hybrid interpolation function itself. The curves generated by the hybrid interpolation function. Remember that we also have the blending function that blends the consecutive interpolation functions. Now, the coloring scheme here is such that if the hybrid interpolation function is using circular interpolation function, I color it red. If it's using elliptical interpolation function, I color that segment blue. And because we're blending between neighboring interpolation functions, in some places you're going to see some blending between blue and red. So that means we blend a circular interpolation function with an elliptical interpolation function. So as you can see here, in most places, it's favoring the circular interpolation function where we have that angle that I talked about is larger than pi over 2. But in some places, it's using elliptical interpolation function, so we're guaranteeing that we're getting nice curves. So what would happen if we just use the elliptical interpolation function everywhere? Well, here's what would happen. We're going to get some strange curvature spikes, right? So like in this, over here is one example that I'm going to be highlighting right up here. But it's not just there, there are other places too, like over here, for example, up there. So like the curve doesn't look very smooth because it has these curvature spikes. And if you look at the control point data, I mean, those strange curvature spikes, they're not in the control point data, right? So if you were to use elliptical interpolation function for designing some shape, you kind of need to be very careful about how you place the control points. And even so, you may not be able to avoid these strange curvature spikes, because as you add more control points, you're going to get more and more curvature spikes. It's really annoying. But the hybrid interpolation function completely eliminates that. Okay, what if we do the opposite? We just use circular interpolation function. In which case, I mean, most places are fine because remember the hybrid interpolation function actually favors circular interpolation function. But in some places, I'm getting deviations from the control polygon, like over here in this example. As you've seen in the previous example, circular interpolation function can really do catastrophic things. This is not catastrophic, but not something desirable. Actually, also I'm getting these, undesired shapes over here and there, but depends on whether or not you want to get them. Nonetheless, circular interpolation function, we know that it's going to do crazy stuff sometimes, so we really want to avoid it. If you use the Bezier interpolation function, well, actually this is fine. There's nothing technically wrong with it, but maybe the only thing you can object to is that we're not getting any circular features. So if you want to get circular features, this this Bezier interpolation function is not going to be the right interpolation function for you. For example, look at the eyes over here. With the hybrid interpolation function, I'm getting nice circular features, but with Bezier interpolation function, I'm not getting nice circular features. So let's take a look at circles again, just to stress this point. So here's 4 control points placed on a circle. Of course, this doesn't look like a circle. If I add more, maybe this looks like a circle, maybe, but if I remove the control points, you should be able to see that this is not a very smooth circle, right? So it's like, doesn't quite look right. It's bent just a little bit. So it's not a very close approximation to a circle, even with 8 control points. You need to add more and more control points to get some close approximation to a circle. Well, if we use elliptical interpolation function, we're not getting something great either, right? We have these spikes. That's not so great either. Of course, if you use circular interpolation function, you get circle, whatever you do. So it's always good. If you want to get circles, that is. But even in this case, we're getting a circle, which is kind of odd, right? Like, why would I get this piece? This is kind of odd. With hybrid interpolation function, we pretty much get a circle whenever a circle makes sense, and whenever a circle doesn't make sense, we switch to elliptical interpolation function, right? So that's hybrid interpolation function is giving us pretty much what we want. So another example in prior work, the last example in prior work that I mentioned. Oh, I just lost my camera. This is really unfortunate. The last example is I'm going to just show you. I went over time and my camera ran out of battery, so I'm just going to show you the slides from this point on. So the other example interpolation function that existed in prior work is this one, using rational Bezier formulation, very similar to our formulation. But if you compare it to our Bezier interpolation function, it's getting these undesired self-intersections and deviations from the control polygon, which is, not so great. But the reason why it's getting this is that these curves are not very carefully designed. So if you were to carefully design these curves such that, you just do what we did for designing the Bezier interpolation function. That is, we place the middle control point to the local curvature maximum, right? So if you do that with these curves, actually, I think that would be fairly reasonable. We would get a nice curve. But unfortunately, these curves defined in prior work are not doing that. They're doing something simpler, and that simpler thing doesn't really lead to nice looking curves in the end, or curves with nice properties in the end. But the very concept of using rational Bezier, it's not bad. It's just adding an extra dimension that I personally am not a big fan of, but there might be applications where this could be pretty good. All right, moving on. Now, as I said, kappa curves was a big motivation for me to start working on this topic. So let me show a direct comparison to kappa curves here. In this case, the curvature spikes here at these control points, you may not like them, but there's nothing technically wrong with them. They're still G2 continuous at that point. They're fine. If you zoom in, you'll see that they're smooth. What is worrisome about this formulation, what's a lot more worrisome about this formulation, is it's a struggle with generating
linear segments. So the pieces where they're supposed to be linear, they're not linear, they're bent. And they're bent because the numerical optimization is such that it's trying to create a curvature maximum. So it's trying to create curvature maxima at the control points. And if you have a line, you're not going to get a curvature maxima at the control point. So it's basically the numerical optimization it's trying to solve is causing it to avoid generating linear segments, which is unfortunate. In our case, all of the interpolation functions will be able to generate perfect linear segments, which is not a problem at all. Another problem here is that, of course, they're only 2D. You can't really extend them to higher dimensions. Well, maybe there's a way to do that, but there's no trivial way of extending them to higher dimensions. So if you look at higher dimensions, let me show you some 3D examples. In this case, this hair model. The hair strands are defined by curves using the hybrid interpolation function. The hair mesh you see on the left side is also generated by curves that use the hybrid interpolation function. So basically, you can use them in 3D. And so I can actually do a live demo now. So there's a live demo on my webpage. You can try it out if you want to. But since this is a live talk, so maybe I can do a live demo. Let me switch to it. Okay. So feel free to go to this link and play with the demo if you want to. So in conclusion, I ended up describing a class of curves and all curves in this class have C2 continuity and local support, and they don't require any numerical global optimization. And the local support is just an inherent of their formulation. And the examples in this class have that show that we can generate curves that have no self-intersections, they have well-defined bounds, and we can get perfect lines and perfect circular arcs. So these curves are actually very, very nice. Actually, of all the curve formulations that I know, the curves with hybrid interpolation function, these curves with hybrid interpolation functions are going to be the curves that's going to be the formulation that I would recommend if you're interested in using curves with C2 continuity, interpolating curves with C2 continuity. But if you want to have interpolating curves and you don't care about C2 continuity so much because your application maybe did not demand it, there are other options. Like one example is the HPG paper that we presented this year. That's Neutron's work in collaboration with Larry Seiler. So in this case, we're showing that we can get 3D curves using quadratic polynomials, quadratic Beziers, if you will, and get some as opposed to cubic Beziers. So we can take cubic Beziers and convert them to quadratic Beziers and get some performance boost that way. But of course, these curves are going to be C1, they're not going to be C2. So if you want C2 continuity, they're not going to be very, very helpful. In terms of future work, what I'm thinking in this is a it's a new topic. It's a new curve formulation. There might be lots of things to explore. One obvious thing to explore, I think, is different interpolation functions. So I think about this as like application specific curve formulation. You can define an interpolation function that's suitable for your application and use that. But if you don't, now if you can come up with some application specific interpolation function that will that makes sense for the application. If you don't know what to use, then you can just go ahead and use the hybrid interpolation function. That's actually doing a very, very good job. But yeah, it'll be interesting to try out different interpolation functions and try different ways of connecting 3 points in space and see what kind of nice properties we would get from these curves. So with that, I'd like to thank Scott Schaefer. He gave me very nice comments about the formulation. We had some nice discussions on that, and Zipeng Yan helped me with the copper curves implementation. ZoomUXL prepared some nice artwork with these curves, and Lee Perry Smith prepared the model that I use for the 3D hair models. And I would also like to thank the anonymous reviewers, especially the one that pointed out that earlier tech report to me that was super helpful. So yeah, this is a longer version, much longer version of my SIGGRAPH talk with a bit more details. It was too long, especially combined with the technical issues I had before we started, such that it sort of drained my camera's battery. So I apologize for that. But I'm here. I haven't disappeared really. Well, I visually disappeared, but I'm here, and I'm happy to take any questions that you guys might have.
So there are a couple of questions on the YouTube chat.
Oh, Dachi, go ahead, please.
Yeah, so Thomas Bronner asked, how does a reparameterization of a curve looks like to get constant speed when evaluating? I want to move along the spline with constant speed.
Oh, constant speed, that's hard. Constant speed, strictly constant speed is not easy, actually. Just as a general problem for interpolating curves, actually as a general problem for any curves. getting constant speed. It's so I'm not sure. So for most curve formulations, I don't think you can just reparameterize it such that you get constant speed. So as I recall, I looked into this, a long time ago. I can't quite remember how I proved it to myself, but as far as I remember, it's not possible to get a reparameterization of any cubic polynomial or quadratic polynomial that will give you constant speed. But what you can do is that you can compute the speed of the parameter and then adjust how fast you're moving along the curve with that. So you end up, and if you include that, you will end up having probably having a higher degree polynomial, or maybe a rational polynomial, some sort of rational polynomial that will give you the same shape but different, but adjusted speed. So yeah, that's not easy, and you're not going to get it just by reparameterizing the curve. But you might be able to get it by you can compute the speed of the parameter along the curve, and then you divide by that speed, and you adjust how fast you're moving along the curve. So there are ways around it, but it's kind of it's not very simple.
Okay, thank you. So
This is a very general answer to any kind of curve. Actually, it's not specific to these curves.
So there's also a question from Marshall Laufstein. I think he asked about can I blend different types of splines? I think that's obvious because your hybrid curve is blending this circular with the elliptical interpolation function.
Yeah. So consecutive interpolation functions, they don't have to use the same formulation. They could be anything really.
Okay. So and there's also the question. Actually, that's a question not for you, but probably that you can also answer them. So perplexed moth asks, what are the most common or typical applications of splines are you guys using them for? So I'm a hobbyist programmer, so I use them for graphical effects and games. So could you share your experience of using these splines? So can you illustrate some different applications that would benefit from your new technique?
Okay. Well, so the application that I try to stay away from applications in this paper because curves have a really wide range of applications, and these particular curve types could be used with any of them, pretty much any of them. But there are I can list a number of applications. Well, I had to show a few applications at least for like curve drawings. Could be CAD drawings, or could be drawings for artistic purposes. Any kind of vector drawing, you can use curves like this. There are we use curves. Imagine SVG files that could define web pages or any 2D graphics or 3D graphics that involve curves, of course. Beyond that, another example that I showed was a hair model. That's definitely a valid example. The hair models are typically defined as curves. Yarn level or fiber level cloth models are also using curves. It's pretty much the in the similar in some ways, or models like grass and anything that looks like a collection of fibers. Really, you can represent them using curves. But there are applications that look nothing like that. For example, one thing that annoys me is that when I'm using some applications to draw to draw a graph, so I have some data points, and I would like my application to smoothly interpolate those data points. The curve that application forms that interpolates these data points. Now, I'm just trying to draw a graph for various purposes. Sometimes that curve doesn't quite look representative of my data points, and I find it quite annoying actually. So if you were to use curves like the ones that I defined, they would actually form an interpolation that's not going to have visually recognizable features. So that would be pretty nice for applications of that kind. So those are the applications that come to my mind immediately. But these are very general concepts, so I'm pretty sure there are numerous applications that I can't quite think of at the moment.
Oh, thanks. So Cardi also asked a question: could this include some form of control handles if one is mostly happy with the interpolation but want to tweak a small part?
Okay, this is a very interesting one. I'm gonna say yes and no. So I'm saying yes and no for two reasons. Well, for the reason is that the reason is that it really depends on the type of the type of interpolation function you're using. So let me let me clean this up. So if you are using any of these interpolation functions, yeah, they're not going to give you they're not going to give you any Bezier handles or anything like that will allow you to control the shape of the curve. So the only option here is that you sort of carefully place two control points close to each other. So this sort of gives you something that kind of looks like a Bezier-like behavior here. Not quite. I'm defining data points that the curve goes through, but I can define sort of like the tangent direction by putting two control points together. Actually, that's the trick that I used. Like if I wanted to have a line between two control points, I just need to put 4 consecutive control points along the same line, and then I get a linear.
So show your slides, not the browser window.
Oh, shoot. Yeah, thank you for telling me this. Okay, now you should be able to hear me on YouTube. So I did a silent demo. So this is the one. All right, let me quickly go over the stuff that I talked about. So I was saying that no, we cannot directly define the tangent, but by strategically placing the points, we can sort of indirectly control the tangent of the curve by placing control points close together. All right. And the other thing that I was just talking about is the fact that we can't get nice subdivisions with actually any kind of interpolating curves. With Bezier curves, if this was a piecewise Bezier curve, then you know I could just subdivide it into smaller pieces and I would get exactly the same shape. But with any of the interpolating curve formulations that I've looked at, we won't be able to get perfect subdivisions. So it is, I think you can take the definition, you can take the formulation of kappa curves and maybe come up with a way of, well, kappa curves are not going to work, but maybe there's a way to do a global optimization that will give you exactly the same shape so you can get subdivision property. But you know, with these kind of curves, we're not going to get subdivision property. So when I add a new control point between the control points, like I add a new control point here, I'm not going to get exactly the same curve shape. I can approximate it by placing it in strategically placing it such that I'm sort of getting something that more or less looks like it, but it's not going to be exact. So that's one thing that I don't like, but turns out when you require local support, when you have local support, well-defined local support, you're not going to get subdivision property with interpolating curves. So it's a limitation of all interpolating curves, not just these particular interpolating curves. That's the one thing that I'm not happy with, but all other properties of these curves are actually very, very nice. So finally, we have an interpolating curve formulation that we can happily use. So I believe everyone is seeing my demo and hearing my voice, so we're okay now, and I believe we're at the end of the questions, right? Daji, are there any more questions?
I have a quick question.
Oh, go ahead, please.
I'm asking on behalf of an interested colleague who couldn't join the Zoom, but he's asking if you thought about how hard it would be to intersect a subversion of these curves with a ray.
Oh, very, very good question. Right. So one of the interesting things to consider at this point is how would you do rendering with these curves? So this application is using rasterization for rendering. Yeah, it's rendering them similar to how you would render Bezier curves with rasterization, basically splitting into smaller pieces, and every curve piece is defined by many smaller tiny pieces. Now, how would you do ray curve intersection with these curves? Actually, you would do exactly the same way that we're doing with cubic Beziers. Well, maybe there are better solutions. I'm not sure. That's something to be looked at in future work, I think. But currently, the way we're handling Bezier curves is that when we use cubic Bezier ray intersection, turns out it's not mathematically that easy, so we're solving it numerically, right? You can use phantom ray intersection, or you can use the closest point to the curve formulations. They're all using some sort of numerical method to find the intersection point by numerical iteration. The same thing applies here. Actually, for the hair example that I showed, I have implemented ray curve intersection exactly like this, and that was not hard to do at all. Let me switch to that. that was all right. So this is not this is rendered using rasterization, but it could be rendered using ray tracing as well. It looks exactly the same. And you know, I just took my Bezier ray intersection routine, and instead of Bezier curve, I replaced it with this curve formulation, and it worked fine because that function was using numerical iterations anyway. So it doesn't really care how you define the curve, basically. And I think this applies to pretty much every practical ray curve intersection routine that I've seen. So hopefully that's an answer to your question, Tim.
Thank you.
Cardi just posted a question on YouTube chat.
Uh-huh.
So in terms of compute, how does it compare to Bezier, performance-wise?
Performance-wise, well, these are very fast, right? Because evaluating these curves are not expensive at all, but there is a bit of an initialization cost. That is, for example, if I want to use Bezier interpolation function, I need to find where to put the middle point, right? So I need to solve a cubic equation. Same goes for elliptical interpolation function. I need to solve a cubic polynomial to find the ellipse. And of course, since elliptical interpolation function is used in the hybrid interpolation function, in this example, I'm also solving for those. So whenever you move a control point, you're going to have to recompute those terms for the neighboring control points. So there is a non-zero initialization cost. But once you initialize them, once you know exactly how the parameter, once you know the internal parameters of your interpolation functions, then the rest is super cheap. The blending function use sine and cosine, so maybe it's not as cheap as a polynomial, but today's computing devices, you won't notice the difference. So the only cost here, the only noticeable cost here is the initialization cost. So when you generate your interpolation functions from the control points, so for a model like this, when you have more than 100,000 hair strands each with I don't know how many curve pieces. So that's a lot of cubic equations to solve. You can notice the performance difference, but it's still very fast. You can just notice it with a model like this. Although maybe there are ways to have it. I didn't have a highly optimized code for this, so maybe that's why I was noticing that it was getting maybe a little slower. Maybe I don't want to put a number to it because it really depends on the application. But there's a non-trivial cost there. The rest is quite trivial.
Okay, thank you. So there's a new question on YouTube chat. So what are the benefits of using C2 interpolating splines for hair? Why the C2 community would be required for hair specifically?
That's a very good question. For hair specifically, I am not 100% convinced that it is required. It is nice to have C2 continuity because that means you can see my mouse pointer, which is nice. I believe you can see it anyway. So when you look at the specular regions here, the shapes of these speculars are going to be continuous. So that's going to be the nice thing about it. Without C2, these are not going to be they're going to the shape of the speculars are going to be discontinuous. So it's not like I'm going to have a specular region and then it's just going to cut off to another specular region, but it's not going to smoothly change. Although it's going to continuously change, it's not going to smoothly change. So, but there are different degrees of continuity, of course. So that's the one thing where you can get something that is theoretically nicer, but in practice, personally, I am not 100% committed that that Hare models must be defined with C2 continuity. I think C1 continuity is definitely required. Yes, there's you definitely want to have C1 or at least G1, but C2 maybe. So I'm personally not convinced that they're required. That's why I cannot convince you that they are required.
A question on Zoom. So there's kind of a sort of discontinuity when you're deciding between whether you're going to be using the circular interpolation or the elliptical interpolation, right? So this is like with respect to the control points. Like, say we're taking the gradient or derivative with respect to the input control points. Is that like a thing? Like, is there going to be some sort of discontinuity as a result of making the choice between circle or ellipse?
Oh, that's a very good question. Okay, so actually, that's a very good point. Let me. You guys are seeing the demo, right? So as I move my control point, so this curve piece is going from red to blue, meaning I'm switching to elliptical interpolation function. So the nice thing about these two interpolation functions, the elliptical interpolation function and circular interpolation function, I'm just going to show you these two. At the point where the hybrid interpolation function switches between the two, they will be producing exactly the same curve. So that's why there is no discontinuity of switching between these two interpolation functions. Just to be perfectly clear, the interpolation function that I'm using, the two consecutive interpolation functions can use whatever function they want. It's blending function will blend them together nicely, so we won't have any discontinuity there. But when you define an interpolation function that combines two interpolation functions, that combines two functions together, then you need to make sure that that interpolation function itself behaves nicely. And the hybrid interpolation function behaves nicely because I'm not sure if you can tell, it's very hard. But these two interpolation functions, circular and elliptical interpolation functions, will produce exactly the same circular arc at the point when I'm switching between the two. If that is not the case, if I'm trying to form a function that combines multiple functions that are not exactly the same at any point, then I can just blend the two of them. I can sort of interpolate the result of the two, so I can smoothly interpolate between them to make sure that I'm not going to have any jumps. But that is actually very, very important. When you're switching between formulations, you need to make sure that it's continuous.
Okay. So yeah, I can see that like it's gonna be like at the very least C0 or like C1 continuous with respect to the input points that you're interpolating with. I was just curious if it would also be like C1, C2, or maybe even C3 continuous.
All right, so there are different forms of continuity. The kind of continuity that I was talking about when you're switching between circular interpolation function and elliptical interpolation function, that's the continuity in time, if you will. So if I'm moving a control point, the curve is not jumping from one shape to another shape. So that shape changes continuously, right? But if you look at the resulting curve, and the continuity properties of the resulting curve, you are guaranteed to get C2 regardless of what you do. As long as you define a valid interpolation function you're going to get C2 continuity regardless of the other properties of your interpolation function. So that's guaranteed by this class of C2 interpolating curves will guarantee that the curve itself will have C2 continuity.
So when you're talking about like with respect to time, is that like the time on the curve?
No, it's not time on the curve. Here's what I'm talking about is if I take a control point and move it around. So there's no discontinuity here in the sense that if I go from this point to a point right next to it, I get a completely different looking curve. The curve is not jumping from one shape to another. Right. Actually, with the circular interpolation function, let me show you that. With the circular interpolation function, it is possible to go from one shape over here, goes to infinity, and goes to negative infinity. So it's actually going from one shape to another. It is technically continuous, but you see, like, I'm making a very small change and the curve shape changes drastically. But I think in this case, well, mathematically it's fine, but also the curve itself is going to infinity. So I guess it's sort of expected that its shape change is going to be huge. Right. So that's what I mean by time. I'm moving control points.
That makes sense.
Any other questions, comments, complaints, suggestions, anything? All right, I guess we've exhausted everything, and we're also exhausted my ability of getting technical problems. I got all technical problems that I could possibly get. So before I invent a new kind of technical problem, let's end it here. Thank you all for joining in, joining to this call, and we're gonna have a different talk next week. The graphic seminar will continue. So, well, thanks again.